This video is on Factorial ANOVA, or put another way, this video is focused on comparison of means analyses when control variables are involved. Honestly, this is one of the less likely sets of tools you'll use if you're doing applied statistics in a practical setting. It's more appropriate to circumstances in experimental research. And so it's possible if you do a program intervention at some organization and you want to see if that program makes a difference and you're doing before and after measures, then this might be the right tool. You'd go to some sort of Factorial ANOVA using repeated measures. But that's not really commonly done. So this is probably not the tool you'll use the most often. Nonetheless, this is going to be a tool that's going to inform you in certain ways about the way controlled analyses work. Take that knowledge you have forward so that you can better understand some tools later. There are a number of previous videos in this series that I'm assuming you've watched and understand before you can work with this one. You definitely want to understand what I'm trying to do with the framework. You definitely want to understand the JASP program if you want to replicate what I'm doing here on your own with your own data. You have to understand shape, strength, and significance, the way that I use those terms and what I mean by them. You also have to have watched the specification video, which goes forward to say, why do we add statistical controls? Now, I use the word specification in a somewhat different way. I'm in keeping with what is custom within the field, but I use it in a somewhat different way to simplify this and help you understand what you're doing with statistical controls, so it becomes particularly relevant here. And you're going to have to understand something about central tendency and dispersion measures, since they're at the heart of comparison of means. And you're going to have to understand the bivariate comparison of means reality before you can go on to use this multivariate approach. So all of those videos are previously published in the series, and I'm assuming you've watched all of them and understand all of them before you step into this one. The framework that I'm using, remember, has three pieces. There's a simplified choosing grid to try to get a statistical tool set that is appropriate for the kind of data you have. And then once you've run the analysis with that tool set, the intention is to be able to look for the right things that statistics can do to be able to answer a practical question. And then, once you have found the results that do those things you need done with statistics, you need to figure out how to report that information either in publication or in presentation, and I have the 5 guidelines that I use for reporting the results. So this whole framework now, if we're going to look at it for Factorial ANOVA, we actually find that we have to start with something bivariate. So this is a set of analysis questions that we used in the last videos as age in ordinal categories related to watching television, and now I'm going to add is degree attainment related to watching television. And what I want to do is I want to see how much they matter in predicting or being related to television watching, having controlled for the other. That will be the new part of this. Again, using that 2018 General Social Survey dataset I've used in the previous videos, and the variables that I'm going to work with are TV hours, age collapsed into categories, and degree. So you'll recall that the measure that we had for TV hours ranked from 0 to 24 as measures of hours, and then it also had measures of 98, 99, and -1 that were for non-valid data categories, and those will need to be removed. Also, from the code book, we can see that degree has values of 0, 1, 2, 3, and 4 that are valid, a 0 meaning that the person has less than high school degree, a 1 meaning they have a high school degree, 2 meaning they have an associate degree or some junior college, 3 meaning that they have a bachelor's degree, and a 4 meaning they have a master's or other advanced degree. 7, 8, and 9 stand for don't know, no answer, and not applicable, not quite in that order, but 7, 8, and 9 are non-valid categories. But notice that those codes, if you look to the right there, those codes actually have no cases in the 2018 data. So I don't care. since nobody has a value of 7, 8, or 9, I don't need to worry about removing those. And that's really helpful because some people did say 7, 8, or 9 hours of television watching. And so now to remove them from one variable and not the other, I would have to go in and either use a filtering on a particular variable or go into the actual Excel version of the data set and remove and delete certain values. But don't have to worry about it because of the way this is set up. All right, so our first two questions are, is age related to watching television, and is degree related to watching television? Now, this is the material from the last video. This is basically one-way ANOVA. And so we went through the process and we recognized which row we had to work with and which column we had to work with and the kind of independent variable that was involved. And then we gridded out and found that we were doing comparison of means in a two-variable analysis, and we needed to report shape, strength, and significance. So we need these bivariate results here before we can carry on to do multivariate, and you'll see why when we get later in the presentation. All right, so we have all these normal assumptions, no missing data, no serious outliers. There is list-wise case deletion coming. I put it in parentheses because you don't have to worry about this. It just happens in the process of the analysis. What actually happens here is that the program, when it takes the different variables that you're working with and it puts them all together into one analysis, it only includes the cases that have values on all, the full list of the variables. The alternative is something called pairwise, even though you have multiple variables in the actual mathematical analysis, all related to each other. Pairwise only looks at a couple of variables at a time in terms of which cases it removes. That is far less common and introduces a bunch of different problems. So if you're doing bivariate analysis, well, of course it's pairwise. There's only two variables. But when you're doing multivariate analysis, by default, the programs will always use listwise deletion because it's listwise deletion that gets only the cases that we need for that particular analysis. We talked about parametric statistics and the parametric assumptions that are involved in comparison of means. Those still apply here as well, although both are beyond the capacity of this video series to really help you understand with depth. All right, so what I'm going to do is I'm just going to quickly look at the results. There's no reason to run these in JASP, but the last video did this. But I want you to recognize that when we look at the relationship between watching television and age and categories, you can see that this is a statistically significant result. The p-value is below 0.05. That this is a weak effect. About 4.9% of the variation in TV hours is predicted by the age variable. And you can see that the 18 to 29-year-olds on average watched about 2.6 hours, and then 30 to 44-year-olds 2.2 hours, 2.8, 3.5, 4.0. So 2.6, 2.2, 2.8, 3.5, 4.0. It starts a little higher with 18 to 29, but in general, these three younger age groups are roughly the same, 2.6, 2.2, 2.8. And then you go up to 3.5 and up to 4, so older age cohorts tend to watch more television on average. Similarly, as was shown in the last video, we could talk about the extent to which there's dispersion amongst the cases. There's more dispersion amongst these 18 to 29-year-olds. All right, so that's what we find when we consider the relationship between age and television watching. That's going to matter when we do our multivariate work. Now, here are the results looking at how degree is related to it. We could see that less than high school, on average, those folks with less than a high school degree, no matter what age, this is just looking at degree, people with less than high school tend to watch about 3.6 hours. People with high school degrees tend to watch about 3.2 hours. Associate or junior college, 3.1, bachelor's degree, 2 hours, and graduate degrees, roughly 2 hours as well. So as people get more degrees, they watch less. This is a weak effect as well. 4.5% of the variation is explained by degree, and it is statistically significant. We can reject the null. We think something is happening here. The null is probably not true in the larger population. So that brings us to the analysis question we care about with Factorial ANOVA. How much relation to television watching does each of these independent variables have after controlling for the other? What's happening mathematically is that they're going to all be put together into one mathematical process, and that mathematical process is going to remove the effects of one, remove the effects of age, and see how degree still predicts or relates to the television watching behavior. And it's going to remove the effects of degree mathematically, the variation in degree levels, and it's going to, in essence, treat everybody as if they have the same degree value, and then it's going to see if age is related. If degree didn't matter, does age matter for predicting television watching behavior? All right, so this is a new kind of situation where we say, are we looking at a one variable analysis? There are three variables named here: television watching, age in categories, and degree. We could do three one variable analyses and never relate them. That's not what's being asked for here. We could do a two variable analysis. We could do a couple of them. In fact, we just did them a moment ago. We just showed the results from them. Or we could do a multivariate analysis where we're actually using all of the patterns in the data from all three variables in one mathematical process. And that, of course, is what we're going to do here. And so we're going to be in this row when we choose a tool. We already know from the previous videos that the dependent variable we're working with here is a scaled variable. Television watching is a ratio variable. When we get down further down the list, we find that we have to decide if the independent variables are nominal or ordinal, categorical variables, or if they're interval or ratio level of measurement, which would be scaled. And we recognize that both of the variables that we're working with here, degree and age in categories, are categorical. Age in categories is an ordinal variable. But if we had age as how many years have you been alive, or as some cultures would have it, how many years have you lived in, so you'd get a slightly different age number in some cultures. But all of them count the number of years. They have a 0 point. Well, some don't. Some are interval because they count the number of years you've been alive. So the minute you're born, you are actually 1. Okay, and that would be an interval or ratio independent variable. What are you going to do if you have some independent variables that are categorical and some independent variables that are interval or ratio, and you want to run a multivariate analysis? Well, you're going to use something beyond simple multivariate analysis. You're going to use a more complicated multivariate analysis, which is beyond the scope of what this series of videos will introduce you to. I have set this example up so that both of the independent variables are in fact categorical. And that means that the choice that we make for statistical tool is going to be in that column. So we are now in the cell simple multivariate analysis with a scaled dependent variable and two categorical independent variables, and we use Factorial ANOVA, which means that we're going to be interested in shape, strength, significance, and specification, and we're going to have to explain how each of those is thought about, what we mean by those in terms of what the results tell us, so that then we can report the results in a way that helps an audience to understand the answer to the original question. Let me make a quick comment about these terms. So a one-way ANOVA is just a way of saying you have one independent variable and you look at the means within the categories of that one independent variable. A two-way ANOVA is a way of saying you have two independent variables. Let's say that I had a circumstance where I was going to look at males and females, and I was going to look at, we'll just say, black and white. And so what I really have are four groups: white males, black females, white females. And so those four groups now, within each of them, I will look at the means, and that's a two-way ANOVA. But Factorial ANOVA is basically saying we have two or more independent variables. Now, some folks reserve Factorial ANOVA for only when you have three or more independent variables, but many other folks, myself included, obviously, from what I'm about to do, would say that a two independent variable model is in fact factorial as well. And when they talk about the factors, it's a term from a particular branch of statistical work in a particular field or a couple of fields in academic work, that basically the factors are the variables. Factorial is basically saying the variables, multivariables ANOVA. All right. So I'm going to use the term factorial, even though there is a term called two-way ANOVA, and you may have come across that before. I'm saying Factorial subsumes two-way ANOVA and anything else, three-way, four-way, whatever. All right, back to saying these assumptions that were true for the bivariate, they're all true for the multivariate. And then we're going to look at this in the analysis program. All right. So what I want to do is I want to choose the ANOVA option. You recognize, of course, that I have to be doing ANOVA because t-tests are only going to be good if I have 2 category independent variables, and it only works for a single independent variable. Well, I want to do multivariate controls here, and I want to do this with variables degree that has 5 categories, 0, 1, 2, 3, 4, and for age that also has 5 categories. So I go into my ANOVA. These are not repeated measures because I'm not saying that the same cases were being studied when they were young and those same people when they were old, or those same cases were being studied when they had less than high school and then they were measured again later. I'm saying that the people who are young or the people who are old are different groups of cases. So I'm not doing repeated measures. All right, so here we are. I need to go ahead and grab the dependent variable, the 273 variable that we've been working with in the previous video, so we're familiar with that already. This is the TV hours. So I'm going to go ahead and put my variable 53 degree in as one of my fixed factors, which is just saying that it's a categorical variable. Factors are variables. Fixed means it's categorical. There are techniques analytically that allow you to mix scaled and fixed or categorical variables together into one set of independent variables. It's beyond the scope of this video series, but they do exist. Now, you can see that I now have the bivariate results for degree and TV hours, and it shows what it showed before. But I needed a few more things. I said that I also wanted, because I wanted to be able to see the shape of the pattern, I also wanted some descriptive statistics. I wanted to be able to see the means and standard deviations, because knowing that it is statistically significant all by itself doesn't really answer any practical question. Fine, it's not the null. But what is it? Well, then our best guess is going to be what we found in our sample, and that's what this shows. And I also would like to have an estimate of effect size, because I might look at these numbers and I might say, well, 1.9 seems like a really big difference from 3.6. So, wow, there's a big effect. Well, we have more standardized mechanisms for deciding strength of effect, and so I'm going to use eta squared and say 4.5% of the variation in TV watching is predicted, is accurately explained mathematically by degree. All right, these are the results that you already saw that I showed you just a moment ago. But I want to see what effect degree has, how well it predicts television watching behavior after taking away the effects of age. Maybe I think, well, people get degrees when they get older. And so I want to find out if I control for age, is it really that I'm finding the age effect here? People with less than high school maybe are younger, and people with bachelors are older than that, and people with doctorates are older than that. And so maybe this is just a proxy for age. And if I could control for age, take away the effects that age has on the television watching behavior, maybe I would find that this doesn't matter. That's what we want to do. And likewise, we want to find out if age, having taken away the effects of degree, continues to matter to the same extent that it did before. Or even potentially, though this is rare, it might show that it matters more, that something was being masked by or suppressed in the results by some other variable we needed to control for. So let me go ahead and grab that age variable. And let me drop it in there as well. And now we have a whole set of results. These are the factorial analysis results from a two-way ANOVA that I want to unpack these and explain what it is that we're seeing in each of these. All right, let me jump back then to my discussion here. Now, the 5 guidelines say that you need to describe the pattern in words, provide statistical evidence, stay true to the cases, stay true to the measures, keep interpretations separate. And in previous videos, we've seen that when you describe the pattern or provide statistical evidence, you do both of those for shape, you do both of those for strength, you do both of those for statistical significance. And now we're going to add specification. But in the specification video, we said there are actually 4 things you might be doing when you add control variables. You might actually gain some understanding of what are called net effects. You might gain some understanding of what we could call collective effects. You might understand something about interaction effects, and you could gain insight into how to specify the model. Where do you think these variables all fit together in the way reality works? So let's unpack with our Factorial ANOVA where we see each of these things happening. All right, so here are the results of the Factorial ANOVA in terms of the f-tests. You see here that we have an f value. We haven't talked about the math, what a sum of squares is here, and what the degrees of freedom are, and what the mean squares mean, and there's something that gets put into a ratio of something to something, and we end up with f values, and then we plot those f values out on a sampling distribution. We haven't talked about any of that in this video series, though in a stats class you've been exposed to those pieces of information. And then that leads us to plot these values, these f values, onto a distribution that lets us decide how likely it is that we would find these results if the null was true in the population. Well, the chance is exceedingly small for degree. It is even after the controls we can see what happens, even after the controls for degree, we can see what happens with age. That's what this is going to tell us. I'm going to unpack those specific results in a moment, but that's what we're seeing here. This, we're going to point out, where we have degree and a multiplication sign, which because of computers has become an asterisk. Degree times age, that's a way of indicating that this is a way of checking if there is an interaction effect. So we'll need to unpack that. And then we'll look at the other things as we get further down the slides. So to make sense of what we see here, particularly these p-values, these top two p-values, and these top two eta squared values, we need to go back and look at the bivariate results, what they were before controls. Okay, so let's start by looking at the numbers for degree. In the bivariate analysis, we found that there was a weak effect. 4.5% of the variation in television watching was predicted by degree. And it was statistically significant. That the null would predict 0 for eta squared. It always predicts zero's trend, zero strength. All right, so there is a trend in that degree is related to television watching, and so we reject the null. But now notice, after we take away the effects for age, the degree number goes from 0.045 to 0.041. Oh, okay. So it's a little smaller, but not much. Basically, there's no change. Degree still matters just as much for predicting television watching behavior after taking away the effects of age as it mattered before. Let's look at the next option. So now, if I compare the results for age, I see that in the bivariate, down at the bottom of the screen here, in bivariate, I had a 0.049 strength, so almost 5% of the variation was explained by age. And we thought, well, maybe what's happening, the way I posed it a moment ago, is maybe degree is really just finding the age effect. If that was true, age would still matter in the controlled version, and degree would not. But instead it's the other way around. What's really happening is a degree effect, and degree is making a difference, and you see that's why it didn't change. But age is not as consequential as it looked like in the bivariate. It's not really explaining 5% of the variation. After you take away the variation being caused by degree, then you find that it only explains age, only explains 2.6% of the variation. Still statistically significant, that's nice, but it's a much weaker effect. So really, if you were going to say, what is the net effect? The effect net of what the control variables were doing, thus the net effects. Then you would say that really degree continues to matter. Age doesn't matter as much. It matters, but it's not as much. And degree is the more important variable here after controls. It has a bigger effect. That's what net effects allow us to do. Crudely put, it allows us to look at some numbers and figure out which variables, which independent variables matter more than the others after controlling for the others. And it turns out degree matters more than age does for understanding TV watching behavior. All right. The next thing we can consider in specification is we can consider collective effects. Okay, and collective effects, now that we've done multivariate controls, and we can see, let me jump back, but you could see for each of degree and age, you could see the strength of effect in what we have, and you could see the significance. We haven't done anything with shape yet. And then you could see the net effects. Collective would be to say, if you, in specification, we sometimes want to know how well this entire set of independent variables predicts the outcome in the dependent. Is it possible that knowing their degree helps us to predict their television watching, and knowing their age helps us predict their television watching, but knowing their degree and their age together collectively helps us to explain even more, right? How much do they, so, what'll happen is, once you control for each other, some of them will have usually a decreasing consequence, because some of what age was seeming to explain in the bivariate was really a degree effect. And once we controlled for degree, the age effect numbers, the eta squared, went down, because degree was what was really happening there. So when you use multiple independent variables and you institute controls for the other variables, then you will find that individually the net effects will show some of them matter less. But you can also talk about how the whole group together now, what they explain. And so in this circumstance, you could argue, not many people do this, but you could argue that we now have explained, instead of the amount of effect that we had from degree being 4.1% or 0.041 as a proportion, or 2.6%, we could say that we've explained about 6.7%. Now that's assuming, here comes a specification argument, that's assuming no other variables need to be in this model. By the very decision to control for just these variables and not others, we have basically specified a model. We have said these are the variables that matter, and other variables don't matter enough to be put into our equation. Well, in truth, what it may mean is we just don't have measures for other things we really want to study. Or it may mean that we're limited analytically and we can't do it for one reason or another. We could run out of cases, and so we start finding we have, instead of just having people, and we'll look at this in a screen to come, but we may have people who have doctorates, or let's say graduate degrees, who are between 18 and 29. There aren't very many of them. Well, if we had people with graduate degrees who are 18 to 29 and who were white, and then 18, 29 graduate degrees who are other races, then we might find we have so few cases that the math falls apart. We do have to have enough cases varying across all these categories. So there are lots of reasons why we might not add more control variables, but by not adding them, even if it's for practical reasons like that, we are implying something about specification of the model, which variables matter. So in terms of collective effects, it's normally not done with Factorial ANOVA. You normally don't report, at least in a simple analytical situation like we're talking about in this video series, you normally don't deal with collective effects. When we talk about multivariate regression in a video coming 3 videos down the road here, we will actually see an example of a tool used specifically to see collective effects. Now, I said that there was this interaction effect number. Now, you may want to go back and you may want to look at the specification video to be reminded about what an interaction effect really is and how they work. But it's basically saying that the two variables together create more of an outcome than you would simply think would happen by looking at the consequences of one in a bivariate form and the consequences of the other in a bivariate form. And those two together, do they do more? Do they exacerbate, or do they augment the effect of each other so that there's a bigger effect, an interaction effect? Okay, these things don't happen a lot. There aren't a lot of interaction effects of huge size, but that's what this model is implicitly doing in this Factorial ANOVA. And so it's represented by showing the variable name times the variable name, and saying they're interacting. And basically, in this circumstance, we're finding that it's not even big enough to reject the null. We don't really believe there is an interaction effect, 0.013. There's hardly any prediction available here. The strength is 1.3% of the variation as explained. So it's basically no effect. And when it's basically no effect, we're certainly not going to reject the null, which says there's no effect. And so we end up saying there's no interaction effect here. If there had been an interaction effect, we could, when we looked at collective effects, actually talk about how that also was part of the collective prediction value of the model. All right, and interaction effects are beyond what we can really deal with well in simple multivariate discussions. It really involves more advanced multivariate kinds of applications. And then finally, we just have this straight up specifying the model. The four things that we can do when we institute controls is we can kind of specify which variables matter by looking at net effects, by looking at collective effects, by looking at interaction effects, and then we can actually start figuring out how to draw a model. And you may want to go back to the video and show, you can see where I showed you that by drawing a bunch of arrows between variable names. Well, what I'm looking at here actually is a discussion of specifying the model. Now, I show it here in two ways. On one side here, I show the means and standard deviations with degree further to the left and age here, and then we have means and standard deviations and the number of cases in each category. And then the other one I have is showing age, and then within categories of age, we're seeing degree. So let's think about what each of these show us. When I look at this table to the left, I'm saying amongst those who have less than a high school degree, what is the relationship between age and television watching? Because I can say for just this group, we can see that it goes from 2.4 to 3.3, 3.2, 4.8, 4.3. Okay, so in general, as you get older, you tend to watch television more. That's what's true for the less than high school crowd. And you can see that pattern just for them. And then you can say, what about those who are high school graduates? And you can look at it and see what the pattern is. What about those who have associate degrees? What about those who have bachelor's degrees? What about those who have graduate degrees? And for the graduate degrees, we see 1.3, 1.6, 2.2, 2.0, and 2.6. So it does increase a little bit as they get older, but not very much. There really is a very small difference here from 1.3 to 1.6, a 0.3 change. Okay, and then we go to 2.2, so a 0.9 change, and then we creep up a little bit. But down here we were seeing movement from 2.5 all the way up to 4.3. So there's a lot more movement. So the effect here is obviously smaller just because there's less change in the means. This way of laying out the table is assuming something about degree and when age matters, and this other one over here is saying, well, if we look within age groups, we can see something about which degree affects the outcome. So we see here that the degrees from less than high school to graduate go from 2.5 to 2.7, 4.4, 1.8, 1.3. So it kind of goes up and then it goes back down for this age group. And for this age group, it goes 3.3, 2.4, 2.2, 1.5, 1.6. So it just goes from higher amounts of television watching to less as degree goes up and so forth. And then you can see in the 75 and older, less than high school watch 4.2 hours on average of television a day, 4.6, 4.3, 2.5, 2.6. And so now we're talking about how much degree matters inside categories of age. And so we're indicating that we think that age is driving this boat and degree has an effect inside categories of age, whereas the earlier one was looking at how degree mattered and age had some effect within the effects of degree. Okay. You probably, honestly, you don't want to mess with this much. But you don't want to really get into trying to, if you're doing simple multivariate analysis and you're working in a practical setting, trying to figure out what this tells you about which variables relate to which variables and where arrows should go in a model. It's not the best use of your time. It's not worth a lot of your focus. But by choosing how you lay out this table, you are making a implied statement. And so you should think about which way you want this table to be read and build it that way. Now, if we jump back over to the JASP analysis, you see that degree comes before age in the example I just ran, and degree comes before age here. In this particular program, I can just literally, I can just go and click on age, and I can drag it and put it above degree and change the layout of the table. In some programs, you may have to take them out and re-enter them to get them in the order you want. But in this particular program, I can just drag them around. Now, in any event, you can see here now how degree comes first and then age, or you can see how age comes first and then degree. And this doesn't change. None of these values change. The F-tests don't care at all how you're choosing to build this model of the descriptive means and standard deviations. Okay, and that's the kind of circumstance that you need to, this doesn't care. So you can basically talk about shape, you can talk about strength and significance before and after controls, and that's great. But when you want to talk about shape, and you want to say, well, what's really going on? And I'll tell you true, there are places where this will happen. I once did a fairly complicated statistical analysis as a consultant, and I was asked to analyze a particular program and its outcomes. And when I got done with that program and its outcomes, this wasn't what I was running. I wasn't running a Factorial ANOVA, but I was running something substantially more demanding than this, because that's what was needed to answer the question that they were asking. And they were really unhappy because they didn't understand what those results meant. So I told them what the upshot was. So here's what it tells you about what's working and what's not working in your program. The outcomes are or are not matching what you want. And they were not happy. And they wanted, one person literally said, well, can't you just give us the results in percentages so that we can understand this ourselves? Well, I certainly can give them percentages, but it won't answer the question they asked about a complicated multi-control kind of setting that they wanted to know about. When you're doing this kind of work, if you're doing it for a boss, if you're doing it to answer a question someplace where you're working, then you can run this F-test information up at the top, the actual, technically the ANOVA, without the descriptives. But you're going to have folks who are going to say, okay, but can you give us actual numbers that describe the actual people? And then you'll end up having to build a table like this. And when you do that, you're going to have to think about which is the control variable and which is the effect variable and so forth. All right, so that's basically the nature of doing multivariate analysis. I want to reiterate that this is not something that you're likely to do a lot of. This is not a tool that you're likely to find yourself using commonly in work settings because you don't normally have a lot of categorical predictor variables and a scaled dependent variable. That's just unusual in most practical settings. What you're much more likely to find yourself doing is to either have all categorical data, independent and dependents, and then you're going to end up in cross tabulations, or you're going to find yourself having all scaled data, dependent variable and the independent variables, and you're going to want to use something that will come up in the next videos. There is a circumstance where you might want to add one categorical independent variable on top of a circumstance where you have several predictor variables that are scaled. So we're going to look at the scaled dependent with scaled independence next. And if you ever find yourself having to wrestle with, I have that scaled and I'm doing that kind of regression analysis, that's where we'll end up. It's easier to drop a categorical variable into regression, learn how to do that. It's not straightforward, but you can learn how to do that easier than you can figure out in a program like JASP and most easily available programs, how to drop a scaled variable into a Factorial ANOVA. So I'm going to suggest this is not where you look first as your way of answering multivariate circumstances, except in this very narrow circumstance with a scaled dependent variable and multiple categorical variables as independent variables. All right, well, that was quite a mouthful. We will carry on in the next video to look at what we do with that circumstance where we have scaled videos both as the dependent and as the independent, and then how we do that with multivariate work as well.